I would like to thank the organizer this my seminar series. Unfortunately, we had some connection issues during the first recording of this talk, so this is a re-recording. And today I'm going to be talking about the soft mode action for the large PSYK model. This is based on a paper that came out in December with my supervisor, Mark Bucca, and also some current work in progress that is happening both with my supervisor again, Mark Bucca, and Alexei Milekin. So first I thought I'd give a bit of an introduction, so motivate our interest or the general interest in the SYK model, talk a bit about the model itself, and with in particular a focus on the low energy limit and the emergent reparameterization invariance that is going to be the focus on of the first half of this talk. So why do we care about SYK? Well, first of all, SYK is a good toy model for quantum chaos. It's probably one of the easiest chaotic models that you can write down. And it has a gravitational dual. This gravitational dual is known as JT gravity. It's a two-dimensional model of gravity. And it describes the near horizon region of extremal black holes. So if you go near the horizon for extremal black holes, your geometry breaks down into this ADS2 times ST minus 1. So, for example, in 4 dimension, this would be ADS2 times S2. And then, of course, asymptotically, you recover either flat space or ADS-T plus 1, depending on which kind of asymptotic geometries you're considering. And if you want to glue together your near horizon region and your asymptotically ADS2 region, you can do so, for example, by this wiggly red line that I've drawn here. And the red line is wiggly because you have some freedom in choosing this gluing. Basically, you have a reparameterization invariance for this gluing that is happening here. This happens because Einstein-Hilbert in 2 dimensions is only depends on the character of the surface that you're studying. And so the Einstein-Hilbert action for all of these reparameterization of your gluing that you're doing here is going to be the same. However, as soon as you add the JT gravity term into your action, then you have an explicit breaking of this symmetry that you originally had when you were just considering Einstein-Hilbert. And I'm mentioning this because this process is exactly identical to an explicit symmetry breaking mechanism that you have for SYK, which is what we're going to be studying over the course of this seminar. The other reason, and this is the reason why we specifically were interested in SYK, is that SYK is a one-dimensional model, so you only have time dependence. However, you can add spatial locality to your model by building a lattice and placing on each lattice side a copy of your SYK model and allowing nearest side interaction. Once you do this, you've built what is known as the SYK chain, and we were interested in studying the chain and in particular in studying the hydrodynamics limit. And this is the work in progress and the second part for this seminar. So what is the model then? What is SYK? Well, SYK is an ensemble of quantum mechanical models. You have M-Majorana fermions with p-body interaction, and your Hamiltonian looks like this. And you have this coupling constant J, which is a random variable that has mean equal to 0 and variance that is proportional to this constant J squared that appears here over n to the p minus 1, where again n is the total number of fermions and p is the number of interactions. So if you want to write down an action for your SYK model, you can do that by using the path integral formalism. And in particular, you can introduce in your path integral collective fields in the following way. So you're just writing one in a very fancy way, and sigma and G are your collective fields. Sigma is the self-energy, whereas G is the fermionic bilinear. And what you can do here is you can first perform your integral in the sigma. And if you do that, you are left with direct delta that basically enforces the fact that G has to be the fermionic bilinear. And then you can perform the integral in G. And of course, if you're integrating a direct delta over all the possible G configuration, this is going to be equal to 1. And I'm going to mention this now because it's going to be relevant later, but if you consider your fermionic bilinear and you take its correlation function, in the free limit or the zero coupling limit, this reduces to 1/2 the sine of tau. And this is simply because fermions anti-commute, so depending on whether or not tau is bigger than 0, you're going to get a plus or a minus sign. And so you introduce these collective fields, and now what you want to do is you want to average over your coupling constant J, and this can be done in a couple of ways. So you can average over your partition function, or, and this is more physically significant, you can average over the log of your partition function, so the free energy. However, at large n, you can show that you get the same result from both of these averages. So for simplicity, you can just average the partition function. And if you do, you find an expression for your action that depends on your collective field sigma and G. So from there, you can write down your equations of motions, and these are the Schwinger-Dyson equations of motion that are right here. So we have that G is equal to the derivative with respect to tau minus sigma to the minus 1, and sigma is equal to J squared G to the P minus 1. And if you consider this equation of motion in the infrared regime, what happens is that this derivative with respect to tau term becomes negligible, and so you can just drop it. And once what you get now is this second set of equations. So the second one is the same as you had before, but the first one becomes the integral over d tau 2 of g of tau tau 2 sigma tau 2 tau 1 equals minus delta of tau minus tau 1. And if you look at this new set of equation, you have an emergent symmetry, a reparameterization symmetry, where you can reparameterize tau as f of tau, provided that sigma and g transform accordingly in this way. So this is basically the one-dimensional version of conformal invariance. And it turns out that in one dimension, having conformal invariance is having a lot of symmetry. And this basically restricts your system to just the ground states and the physics of the ground states, so a topological quantum field theory. However, this is, of course, not really a symmetry for your system, because as soon as you go back to finite temperature, then you still have this derivative with respect to tau that you have to take back into account, because now it's no longer negligible. And if you do that, your reparameterization symmetry is explicitly broken. So if you were to write down a term for your action that breaks this reparameterization symmetry explicitly, and this has been done before, you would find that this term is the Schwarzian derivative. And so a first argument for this was presented by Maldacena and Stanford. They derived it for linearized reparameterizations. So f of tau equal to tau plus some small epsilon of tau. And then they provided arguments to generalize this for generic f of tau. And then there was a second argument, another argument by Kitaev Su. So this result has been known for a while. But we were interested in rederiving this result for a couple of reasons. First of all, this coefficient alpha of s that we have here has been computed, of course, both by Maldacena and Stamford and Kitaev Su. However, the computations that have been provided so far were numerical computations. And the other reason was that, as I mentioned, we were interested in generalizing this infrared regime to the SYK chain, and the previous derivations were not easily generalizable to the chain. So what we did was we considered the large P limit, where again P is the number of interacting fermions, hoping that this would both provide more analytic control and also allow us to generalize this mechanism to the chain. I should also mention that while we were working on this, we found out that another group of people was also working on deriving the Schwarzian for the large PSYK, and they the derivation that they have is similar to ours, but still but it's still a different and alternative derivation to the two derivations I'm going to show you over the course of this talk. So this was our introduction to the SYK model, and now that we kind of know what we're talking about, I can tell you how we derive the Schwarzian action or the Schwarzian derivative. So the first thing I'm going to do is I'm going to tell you how we can take the large P limit for SYK and what we find once we do take this large P limit. And then I will present two different alternative derivations for the Schwarzian derivative. The first one uses arguments from conformal field theories that have boundaries, and the second one consists of coming up with a nice ansatz and plugging this nice ansatz back into the SYK action. So how do we take the large P limit? Well, first of all, I should mention that, yes, we are taking P to be large. However, we are keeping this parameter lambda defined as 2p squared over n to be infinitesimal. The reason why is going to be clearer in a few slides, basically. In the meantime, how do we take the large P limit? Well, we do so by defining another field, the small g, in this following way. So we start from the fermionic bilinear, big G, and we write big G as the sine of tau 1, tau 2 over tau 1 minus tau 2 over 2 times 1 plus G, small g, of tau 1, tau 2 over P. And this is going to be equal in the large P limit, of course, to e to the G over P. So from this definition, there are a few conditions that we need to enforce on our small g. First of all, of course, the fermionic bilinear is antisymmetric, and so is the sine function. So as a result, we need to impose symmetry for small g. So g of tau 1, tau 2 has to be equal to g of tau 2, tau 1. Another thing is that, if you remember, I told you that the correlation function for the fermionic bilinear in the zero coupling limit reduced to 1/2 the sine of tau. So this also, in order for the definition of small g to be consistent with this behavior for the correlation function, we also need to impose that small g, when tau 1 is equal to tau 2, has to be equal to 0. And finally, the third set of conditions that we want to impose on G is KMS, or Kubo-Martin-Swinger. These are conditions that one need to impose on correlation functions for operators in systems at finite temperature, and you get this sort of periodicity in the temperature. So g of tau 1, tau 2 plus beta is equal to g of tau 1, tau 2, and g of tau 1 plus beta tau 2 is equal to g of tau 1, tau 2, where beta is the inverse temperature. So if we put all of these conditions together, this restricts our area of integration quite significantly. So instead of having to integrate over all of tau 1 and tau 2, we just have to consider the shaded green area or the shaded green diamond in this figure here. And this is truly actually a Mobius strip, and I'm going to show you why. So first of all, let's start from this boundary condition. So we have that g is equal to 0 when tau 1 is equal to tau 2. And tau 1 is equal to tau 2 is this line here. However, since we also have KMS, we are going to impose that g is equal to 0 on this other line as well. And this other line is simply tau 2 is equal to tau 1 plus beta. Oh, and I should mention that you in this graph you just see pi and 2 pi. This is because we've set beta to be equal to 2 pi. This is something you're always allowed to do, and then once you want to rewrite beta into your equations and into your theory, you can simply just do so by performing dimensional analysis. So since we're interested in these two boundaries, in these two lines that we have here, it is going to be convenient to define a new set of coordinates as well. So we have delta tau, which is tau 2 minus tau 1, and then we also have tau bar, which is tau 1 plus tau 2 over 2. And this is convenient because the boundaries now are simply delta tau is equal to 0 and delta tau is equal to beta, or 2 pi. Now we still have to take into account symmetry and KMS. And if we do that, and if we combine the symmetry of G and KMS, we find an identification between these 2 points. And so this is why this shaded diamond really is a Mobius strip, because you can sort of close the diamond to make these 2 lines coincide. But before you can do that, since you have this kind of identification between points on these 2 lines, you have to twist your strip before you close it. And in this sense, this is a Mobius strip. I should also mention that there were other possible choices that we could have made for our area of integration. One possible choice, for example, would have been this triangle. However, the shaded diamond seemed more convenient for the computations we wanted to perform, and so this is why we chose the diamond over any other possible choices. And of course, any other area in this graph, in this tau 1, tau 2 graph, can be traced back to our shaded diamond by either applying the symmetry for G or KMS, or a combination of the symmetry and KMS. So this is our area of integration, but what is it that we're integrating? Well, one can get an action for the large P limit of SYK simply by taking this definition of small g and plugging this definition into our large N SYK action, and then taking the large P limit. And if you do that, you land on a Liouville theory in like cone coordinates. And here there is this new field gamma. The reason why, and it's defined as follow. So e to the gamma is simply a rescaling of e to the g, and it's rescaled by this factor. So beta j over 2 pi squared. The reason why this rescaling was performed is that we wanted our Liouville theory not to have any explicit dependence on J or beta, but it's simply a rescaling. And now, as I mentioned before, we can set beta to be equal to 2 pi and then rewrite it back into the theory at a later point with dimensional analysis. We can write a saddle point for our Liouville theory, and it looks like this. So e to the gamma for the saddle point is equal to v squared over 4 cos squared of v times pi minus delta tau over 2, where we now have introduced a new parameter, this v, that is defined here. So we have the beta j is equal to pi v over the cos of pi v over 2. And in particular, of course, we're still interested in the infrared regime, right, or the zero temperature regime. And this would correspond to beta j being large, much greater than 1. But what does this mean in terms of v? Well, beta j can vary from 0 to infinity, as v varies from 0 to 1. And in particular, the infrared regime where beta j is very large corresponds to a limit where our parameter v just goes to 1. And so for us, it's going to be convenient to rewrite v as 1 minus delta v, and then take delta v going to 0. And this is how we can take the infrared regime. I also want to draw your attention to the fact that the prefactor for our Liouville theory is this n over 2p squared. And if you remember earlier, I said, yes, we are taking a large p limit, but we're still taking this lambda 2p squared over n to be small. And in here, we see the inverse of our lambda parameter. So the prefactor for this action is quite large. And this is going to be useful to us in a few seconds. In the meantime, let's talk about reparameterization symmetry. So of course, we still have an emergent reparameterization symmetry at large P. In particular, you can reparameterize tau 1 as f of tau 1 and tau 2 as h of tau 2. This looks like more symmetry than what we started with. This is because we haven't imposed the symmetry for G and KMS for G. Once you do, this symmetry reduces because you have to impose as F is equal to H. And so really, we don't have more symmetry than what we started with. And of course, you have that gamma has to transform accordingly with this symmetry. So gamma gets mapped into gamma of f of tau 1, h of tau 2, plus the log of f prime of tau 1, plus the log of h prime of tau 2. So, of course, then if you exponentiate, this sum is simply going to become a multiplication. So, for example, if you want to write down an expression for the reparameterized saddle and for e to the gamma specifically that you have here, then this delta tau would, of course, be mapped into f of tau 1 minus h of tau 2, but you would also have to multiply this by f prime of tau 1, h prime of tau 2. And for the Liouville theory, in this case, you don't have any terms in the action that breaks reparameterization explicitly. So the action is manifestly reparameterization invariance. What breaks the boundary condition in this case, what breaks the reparameterization in this case are the boundary conditions. So as I've said before, on the boundary, so when tau 1 is equal to tau 2, we need to impose that G is equal to 0. And this means that e to the g on the boundary has to be equal to 1. So if you want to write down the boundary condition for gamma, you have to remember that we have this rescaling here. And if you set beta to be equal to 2 pi, then e to the gamma on the boundary is simply j squared. and or alternatively gamma on the boundary is the log of j squared. And this is what breaks your reparameterization symmetry in the case of Liouville theory, so for the large P limit of SYK. And this was our setup for the large P limit. We can start now deriving the Schwarzian. And I'm going to be starting with the first derivation that uses arguments from conformal field theory. So we start by noting that Liouville theory is a conformal field theory, and it is equipped with conformal boundary conditions. A set of these conformal boundary conditions is the ZZ or Zamologic of boundary conditions. And these tell us that e to the gamma close to the boundary has to behave as some constant mu over delta tau squared. And you can see that these are conformal simply by writing delta tau, like delta tau under reparameterization gets mapped into f of tau 1 minus f of tau 2. And if you expand near the boundary, you find that after reparameterizing this, you still find mu over delta tau squared. Of course, these are not the boundary conditions that we have, because we have that gamma is equal to the log of j squared near the boundary, right? However, if you now look at the saddle point and you consider it in the infrared regime, so you're sending B to 1, and you then expand your saddle point close to the boundary, you find the following expression. So you find 1 over pi delta V plus delta tau squared. So this is almost, right, this easy boundary condition, because you have this kind of like 1 over delta tau squared behavior. If you expand further, you get 1 over delta tau squared minus something. So 1 over delta tau squared is simply ZZ, the ZZ boundary conditions where you set mu to be equal to 1. And so you can interpret this as having ZZ deformed by some operator. And in particular, this operator turns out to be the displacement operator D hat. So this is something that shows up in conformal field theories that have a boundary, because what's happening is that you're breaking translation invariance along the direction that is orthogonal to the boundary. So you can take the OPE for the stress energy tensor close to the boundary, and in this OPE, you find a scalar operator, and the scalar operator is your displacement operator. Its geometric interpretation is that it moves the boundary inward by a unit distance. And if you look at this expression here, you can interpret this, right, as your boundary being moved by being shifted by pi delta V. So the theory that you're studying is a BCFT, so a Liouville theory with ZZ boundary condition plus this small deformation. And of course, you want to consider the contribution coming from all of the boundaries, so you have to integrate over the coordinate that is tangential to the boundary, and this coordinate is this tau bar. So this is what we're doing here. And as I mentioned, the displacement operator is a scalar operator in the OPE for the stress energy tensor. So you can read an expression for D off of the OPE of the stress energy tensor. And it turns out that D is simply the delta tau component of your stress energy tensor on the boundary. So now you have to evaluate D on the correct field configurations. And what are these field configurations? Well, if you remember a couple of slides ago, I told you that yes, we are taking a large P limit. However, we are taking this parameter lambda, which is equal to 2p squared over n, to be infinitesimal. And then we also noted that the inverse of these parameters, so lambda to the -1 or n to the 2p squared, was exactly the prefactor for our Liouville action. So when I said that lambda has to be infinitesimal, what I meant, to be a bit more precise, was that lambda to the -1 times pi delta v had to be of order 1, because delta v, of course, is infinitesimal because this is the limit, this is the infrared limit, and the infrared limit corresponds to delta v being small, or v going to 1. But really then what we can see is that the prefactor, the overall prefactor that we're going to have, so n over 2p squared times pi delta v, is of order 1. So the contribution of any configuration to our action, or really any configuration that is not a zero mode, is quite a big contribution. And what happens is we can basically just set all of these configurations to their saddle points and not consider any fluctuations at all. The only exception for these really are zero modes for our action. And of course, the zero modes is simply the saddle point, yes, but in the infrared limit, the reparameterization of the saddle are also zero modes for the action. And so we also need to evaluate our displacement operator on them. So the reparameterized saddle in the infrared limit is going to look like this. So f prime of tau 1, f prime of tau 2 over the sine squared of f of tau 1 minus f of tau 2 over 2. And if we evaluate d over these configurations, because we can write down an expression for the stress energy tensor that depends on, that is written in terms of e to the gamma over 2. And if we do that and we compute this contribution from this from the displacement operator, we find precisely the Schwarzian derivative, or the thermal Schwarzian derivative. And the prefactor that we have is n pi delta v over 4p squared. And this prefactor is consistent with previous literature results. So the coefficient alpha of s that had been computed by Maldacena Sanford and then Kitaev Su as well is consistent with this n pi delta v over 4p squared. So we're happy because we found the Schwarzian and we found the correct prefactor for the Schwarzian. So this was the first derivation for this action. We now have the second one. And the second one consists of writing down a nice ansatz and then plugging this nice ansatz into the Liouville action and computing. So what is this nice ansatz? What do I mean by nice? Well, we want the configuration that we choose to, first of all, of course, include reparameterization. And we also wanted to obey the boundary condition, so the fact that gamma on the boundary has to be equal to the log of j squared. And finally, we also wanted to obey KMS. So what you can do is you can start from your reparameterized saddle, where you have v squared over 4 cos square of v times pi plus f of tau 1 minus h of tau 2 over 2 times f prime of tau 1, h prime of tau 2. If you impose KMS for your reparameterized saddle, you find, as I anticipated, that f of tau 1 is to be equal to h of tau 1, and then you find this winding condition for f, where f of tau 1 plus 2 pi is equal to f of tau 1 plus 2 pi, where of course here you see 2 pi because we set beta to be equal to 2 pi, but really this is a winding condition that relates to the inverse temperature. Of course, the reparameterized saddle does not obey the boundary conditions. However, if we study the reparameterized saddle in the infrared regime, so for V going to 1, then close to the boundary, your reparameterized saddle is going to obey the ZZ boundary condition and it's going to approximately behave as 1 over delta tau squared. And by observing this, we can then construct something that goes to 1 on the boundary. So specifically, we're considering this ratio. So it's the ratio between the reparameterized saddle and the actual saddle. And if you look at what happened, and this ratio is then computed in the infrared regime, so for V going to 1. And if you look at what happens on the boundary for this ratio, well, the reparameterized saddle is going to behave as 1 over delta tau squared for what we've said, for what we just said in the previous slide. But then the actual saddle also behaves as 1 over delta tau squared. So when you compute the ratio between these two, you find that this is going to be equal to 1 on the boundary. So this does not obey the boundary condition quite yet, but you've built something that just goes to 1 on the boundary. So now if you take this ratio and you multiply this by the reparameterized saddle at finite temperature, the actual saddle at finite temperature, you know that the actual saddle just goes to the log of j squared on the boundary. You multiply by something that is 1 on the boundary, and your whole configuration now obeys boundary condition. And of course, this also obeys KMS by construction and includes preparameterizations. So this is the ansatz we were looking for. And in these two graphs that we have here, we can see on the left the field configuration that we're choosing, and on the right, the saddle point. And as you can see, the field configuration of our choice has a rather different behavior in the bulk when compared to the saddle point, right? However, if you look at the boundary, both the saddle and our ansatz go to 1.5 on the boundary. And this is just kind of like a visual representation of the fact that what we've built is correct. So what you do now is you can take this configuration here. You can plug it into your UV action, and after a rather long computation, you once again land on the Schwarzian, the thermal Schwarzian. And the prefactor is exactly the same as the one we found from our BCFT approach and is once again consistent with literature results. So this concludes the first half of our talk. We've derived the Schwarzian, and from here, as I promised, we're going to build the SYK chain and study in the hydrodynamic limit. So first of all, we're going to see what the SYK chain is and what the Schwarzian regime, the infrared regime looks like for the chain. We're going to then briefly introduce hydrodynamics, and finally, we're going to take the hydrodynamic limit on the chain. So let's start by building the SYK chain. So the idea is, as I've said, you build the lattice, and on each lattice site, you have a copy of your SYK model with your coupling constant J that we have here. And you are introducing a constant J square, right, from the variance of this coupling constant. We said at the beginning that this variance was going to be proportional to J squared. But now you have a second kind of coupling because you're allowing nearest site interaction for the chain. So this means you're taking p over 2 fermions from your site x, and then p over 2 fermions from your site x plus 1. So of course here p is equal to 4, but we're going to be going to the large p limit, so this drawing is just a representation, of course. And you have a second coupling constant, J prime. This is again a random variable. Its mean is again 0, and its variance is going to be proportional to some other constant that we call J1 squared. So in the large P limit, the action for your chain looks like this. So we still have our Liouville, light cone coordinate Liouville action. However, now since you are building a lattice, you have an extra subscript for your field G, this X subscript that you have here, that tells you on which side you are, and then of course you're summing over all of the lattice sides, and then you have your nearest side interaction term, that is this one. So minus J1 squared e to the 1/2 gx plus 1. And from here, you can use both of our derivation to construct an action for the infrared regime. So for the BCFT action, what you're considering are a lot of BCFTs, each on a different lattice site. And the nearest side coupling that we have is simply a bulk operator. For the other derivation, what you do is you take the configuration that we've built, so the ansatz that we wrote down, and you plug it into this action that we have here, and you then compute. In both cases, what you get is the following. So the first line is the Schwarzian, again, the thermal Schwarzian, where you get an extra subscript for F, and you're summing over all of the lattice sides. And then you have the second line, which is the nearest side interaction. So you have the square root of F prime X of tau 1, square root of F prime X of tau 2, and then the square root of sine squared of 1/2 fx of tau 1 minus fx of tau 2 times the same, just with x plus 1. And this is just coming from here, right? Now I should briefly comment on this alpha that we have here. So alpha is simply the ratio between J1 squared and J squared. And if you remember earlier, I talked about the fact that this prefactor here, so this n over 4p squared, is quite large for the kind of large p limit that we're considering. And the only mode that is soft in this limit is this f. So you have this prefactor p delta v that makes the action for f to be small, and this is why you're considering f and not the modes that are orthogonal to it. So now, if we want to be justified in considering this second line for our action and taking this coupling into account, we need this second line to be soft as well. And this means asking alpha to be infinitesimal. So the kind of chain that we're studying has J1 squared to be much smaller than J squared. And these are, again, the variances for J prime, the coupling constant for the nearest side interactions, and J, which was the coupling constant for one single copy of your SYK. And finally, if you write down the equation of motion for the thermal Schwarzian, then the solution for this equation of motion is the following. We have fx of tau is equal to 2 pi over beta of x times times tau. And so if you take the derivative of this with respect to the time derivative of this, so f prime x of tau, this is simply 2 pi over beta x. And you can then interpret this 1 over beta x or Tx as the local temperature. So this is the Schwarzian chain, and now we want to understand what hydrodynamics is in order to then apply it to the chain. Well, historically, the way we've been studying hydrodynamics has always been to just write down an equation of motion and then solve it. So it's a very phenomenological approach. And of course, this is all well and good. However, if you want to consider fluctuation, whether they be quantum fluctuation or statistical fluctuation, this approach does not work. So in more recent years, what has been done is people have been trying to write down hydrodynamic as an effective field theory. So the idea is you have your path integral formalism, you divide your degrees, your UV degrees of freedom, you separate them from your infrared degrees of freedom, and then you integrate out your UV configurations, and you're left with an effective action. And so by construction, the action that you have written down is not going to be local for scale distances smaller than some parameter lambda. And so you can think of your theory basically as a derivative expansion in this dimensionless parameter lambda d mu. And this is sort of the framework in which you're trying to construct hydrodynamics. We're going to be discussing Stringer-Kaldis contours, so I'm also going to briefly introduce those. So suppose you have an operator V and you want to compute its expectation value, then you can write it as the trace of rho of t V, where rho of t is your density matrix, and its time dependence is can be written down in this way. So you have U, which is a unitary operator of TTI, rho 0, which is your density matrix at time Ti, and then U dagger, which is the adjoint of U of TTI. If you want to represent this trace visually, you can do so by drawing a Stringer-Kaldis contour. So you start at Ti with your rho 0, you evolve forward with your unitary operator U, you have your V, and then you evolve backwards by U dagger, the adjoint of U. And since you're taking a trace, this is visually represented by the fact that these two lines here are connected. So the kind of Stringer-Kaldis contours that you're considering are called the closed time path contours. And in particular, you can write down the accelerating functional for correlation functions on these kind of CPT contours. And they're going to be looking like this omega, this W that we have here. And you can then think of writing W in terms of a path integral of microscopic variables, psi1 and psi2. And now you can divide or separate UV and infrared degrees of freedom and integrate out your UV dependence. And you're then left with this path integral over the infrared degrees of freedom, psi1 and psi2, and an effective action, this EFT that we have here. And this is how you can construct hydrodynamics as an EFT rather than just writing down equations of motion. So if we want to apply this to our SYK chain, we sort of immediately run into a problem because, as I mentioned, we want to consider large times. However, in our action, we have a term that is 1 over the square root of a sine squared. And if we want to go to large time to sort of do this derivative expansion approach, well, sine squared is not really well behaved at large time, right? Because it oscillates. So what you can do is you can perform a Wick rotation. And so you start from sine and you land on sinh. And sinh is, of course, well behaved for large times in the sense that this 1 over the square root of sinh square is simply going to be a damping factor. So now to perform our derivative expansion, we can rescale time. And we do so by defining T12 as S over lambda plus minus U, where lambda is going to be our parameter for the derivative expansion that we will consider. And we're considering the following Schwinger-Kaldisch contours. So we're first going forward in time on the real axis and then going backwards. And finally, we're going along the imaginary axis. And now we want to rewrite our f in the following way. So small f can be rewritten as fx, big Fx over lambda, plus minus gx, plus minus lambda qx, plus minus lambda zx. So I'm going to explain what each of these quantities are. So first of all, let's note that now we can sort of average or consider the differences over two different directions, right? We have the time direction, but we also have the spatial direction, which is the Schwarzian lattice that we are considering, so our discretized x. The first quantity that we have here, big F, is an average over both the lattice sides and the forward and backwards time contour. This is our physical variable, physical quantity. The gradient of F is this Gx. So this is, again, averaged over the forward and backward time contour, but it's a spatial difference. Then we have Q. Q is averaged spatially, but it's the difference between the forward and the backward time path. And this is our fluctuation. And finally, Z is the gradient of Q. So this is a spatial difference and also a difference over the time contours. The scaling of these quantities is dictated by KMS, or imposing dynamical KMS. However, as I mentioned, this second part is still a work in progress. And one of the things that we are still working on is gaining an understanding on how to implement dynamical KMS for this chain. So I'm not going to comment on the scaling at all. The one thing that we can say, however, is that the scaling for this big F is chosen in such a way that the difference between f of tau 1 and f of tau 2 is finite or of order 0 in lambda. So here you can see that this difference is just f prime s of s times u. And the reason why we wanted this difference to be finite in lambda is that this is precisely the argument of our sinh. So of course, if this difference were to be small, so if it were, for example, of order lambda, then sinh would also be small, right? And 1 over sinh would blow up. On the other hand, if these were too large, so for example, order 1 over lambda, then the sinh would also be quite large, and we would get a damping factor. So the correct scaling is simply the one that results in a finite difference, and it is the one that we have here. So now that you've defined all of this quantity through small f, what you can do is you plug this definition of small f back into your action. So now you're considering both your coupling action, but also the Schwarzian. You then expand for lambda being small, and you take a continuum limit. And if you do all of this, you find the following expression for your Lagrangian, where we have defined T, the local temperature. As I mentioned before, it was connected to small f prime. And so here it is defined as a derivative with respect to time of big F over 2 pi. And then we also define this quantity V as alpha over 6 delta V. So from here, you can write down your equations of motion and you find the following set. And these are the second equation of motion in particular is consistent with just setting Q to 0. And if you do that, you find that the first equation simply becomes the diffusion equation. So you can interpret Q as noise and set it to 0, and then you recover the diffusion equation. So for the temperature. So of course, this is the classical result. However, you can, first of all, we're happy because it's confirmation that what we've been doing is correct. But then, as I mentioned, this is an expansion in lambda. So this is just the first term of your expansion. And already here, I didn't write it in the diffusion equation, but you have this extra term that is not here classically, and it is the result of quantum fluctuations. And you can go even higher in your expansion, in your lambda expansion, and find even more correction to your classical equations of motion. So this brings us to the end of our talk today. This is sort of all the work that has been done so far. So to recap briefly, we've started by considering the SYK model, and by noting that in the infrared regime, you have an emergent reparameterization symmetry. In order to have more analytic control and to derive the term that breaks explicitly this emergent reparameterization symmetry, we studied the large P limit. And in the large P limit for SYK, you have a Liouville theory on a Mobius strip. And your symmetry is explicitly broken by the fact that you have non-conformal boundary control. From here, you have two alternative approaches to derive the Schwarzian. The first one uses a BCFT argument by considering the Liouville theory, the large SYK, the large P SYK as a Liouville theory with conformal boundary conditions deformed by the displacement operator. And the second derivation that we had was just writing down a nice ansatz that obeyed the boundary condition and included reparameterizations, and plugging this ansatz back into your Liouville action. From here, we built the SYK chain by putting copies of your SYK model on a spatial lattice. And finally, by considering a derivative expansion of the SYK chain, we studied the hydrodynamics regime of the chain, and we were able to recover the diffusion equation. So where do we go from here? The first thing we can, of course, do is, well, we need to figure out KMS. So dynamical KMS, as I mentioned earlier, and we can go to even higher order in our derivative expansions in lambda, so we can find more quantum corrections to classical hydrodynamics. And then what we can do is, or what we want to do is consider autox. This would require a four-fold contour or Swinger-Kaldish contour instead of the two-fold that we saw in a previous slide. And then the other natural direction for this is generalizing this sort of derivation for the Schwarzian to more complex theories, higher dimensional theories. And so this is all I had for you today. Thank you for your attention.